In this video, let us learn ourselves about 4 vectors. Before knowing what is 4 vector, let us know what is Minkowski space. In general, to describe a point or an event, we need the 3-dimensional space. But to make the classical mechanics and consistent with the special theory of relativity, the time is no more considered as an independent variable. So, to keep the special relativity theory consistent, or the classical mechanics to be inconsistent with the special theory of relativity, we have chosen the 4th coordinate as time, and the space which consists of these 4 coordinates is called as a Minkowski space. So the Minkowski space is nothing but it is a 4-dimensional space. 3 our regular Euclidean space, and the 4th one is the time coordinate. So the 4-dimensional space is called as a Minkowski space. Any vector in this 4-dimensional Minkowski space or world space is called as a 4 vector. The components, like in a Lorentz transformation, the component of these 4 vectors transform from one frame to another frame, and we represent this a 4 vector by the notation a mu, where this mu stands for the 4 components 1, 2, 3 and 4. A 4 vector a mu is a vector in 4-dimensional space with the components a1, a2, a3 and a4. In general, we represent it as a mu. And the first 3 components a1, a2, a3 are called the space components, as in case of our regular geometrical space x, y, z. And the 4th component a4 is an imaginary coordinate which is I, a, t, and we call it as a time component. These components transform from S frame to S prime frame in a similar fashion as the Lorentz transformation. So the transformation equations goes like this, and the transformation matrix is 1 0 0 0 0 1 0 0 0 0 gamma I beta gamma 0 0 minus I beta gamma into gamma. Or in general, we can write the transformation equation as a mu prime is equal to summed over nu equal to 1 to 4 a mu nu into a nu. The prime will not come here, it is an written error there, and the transformation equations can be written as a1 prime equal to a1, a2 prime equal to a2, a3 prime is equal to gamma into a3 plus I beta a4, a4 prime is equal to gamma into minus I beta a3 plus a4. These set of 4 equations are called as the transformation equations for the 4 vector. And these transformation equations are governed by the condition summed over mu equal to 1 to 4 a mu prime square is equal to summed over mu equal to 1 to 4 a mu square, or in simple we can write a mu prime into a mu prime is equal to a mu into a mu. The square of the magnitude of the 4 vectors can be simply written as a mu into a mu is equal to a1 square plus a2 square plus a3 square plus a4 square, where a4 is IAT, which can be replaced by minus AT square. So, which also tells that under this Lorentz transformation equation, these 4 vectors remain invariant. The square of the magnitude of the 4 vectors remain invariant. Now let us see some examples for the 4 vector. The first one is the position 4 vector. The position 4 vector x mu is expressed in terms of its 4 components x1, x2, x3 and x4, or in general it is r comma ICT. So this r represents the position vector of a point in the 3-dimensional space, and it represents x1, x2 and x3, which is nothing but it's the space part of the 4-dimensional Minkowski space. And the 4th component x4 is given by ICT, which is the time part of the 4-dimensional position vector x mu. The second example, 4 velocity or the velocity 4 vector, it is represented by E mu, and we can derive its component like this. So it has the four components u1, u2, u3 and ut or u4, where u1 is given by dx1 by d tau, which is rewritten as dx1 by dt into dt by d tau, and dx1 by dt, x1 is nothing but it is x, so it is dx by dt, dt by d tau is nothing but it is 1 by root of 1 minus u square by c square. So dx by dt is nothing but it is the velocity component along the x direction, so it is ux divided by root of 1 minus u square by c square. In the same way, we can derive u2, which is equal to dx2 by d tau is equal to dx2 by dt into dt by d tau. So x2 is nothing but it is y, so dy by dt into 1 by root of 1 minus u square by c square, dy by dt can be written as uy. So the third component is given by u3 dx3 by d tau, again writing it as dx3 by dt into dt by d tau. X3 is nothing but it is z, so dz by dt into 1 by root of 1 minus u square by c square, dz by dt is nothing but uz. So the third component u3 is equal to uz divided by root of 1 minus u square by c square. The fourth component u4 is given by dx4 by d tau. We know the value of x4 is equal to ict, d of ict by dt into dt by d tau. So it is ic divided by root of 1 minus u square by c square, where dt by d tau is given by root of 1 minus u square by c square. Hence, we have found the four components of the velocity 4 vector u1, u2, u3, u4, which can be represented by u mu is equal to ux divided by root of 1 minus u square by c square, uy divided by root of 1 minus u square by c square, uz divided by root of 1 minus u square by c square, and ic divided by root of 1 minus u square by c square. Or simply we can write u mu is equal to u divided by root of 1 minus u square by c square. The fourth component ic divided by root of 1 minus u square by c square. So here u is nothing but it is dr by dt, which is the three-dimensional velocity vector. Our third example is momentum 4 vector. Again, the momentum 4 vector, which is represented by p mu, has four components, and we define them. P1 is equal to m naught u1. So the velocity here for the p1 component is u1. We know the value for it is m naught. u1 is ux divided by root of 1 minus u square by c square, and by the variation of mass with velocity we know m is equal to m naught divided by root of 1 minus u square by c square. So it is replaced by m, so m into ux is equal to px. The same way p2 can be obtained as py, p3 can be obtained as pz. And now let's move to the p4. It is m naught u4. We know the value for u4 as ic divided by root of 1 minus u square by c square, or we can m naught divided by root of 1 minus u square by c square is written as m. So we got imc, or we can write it as I e by c. So this E by c is obtained from Einstein's mass energy relation, E equal to mc square, or E by c is equal to mc. So the four component of momentum, which are given by P1, P2, P3, P4, can be represented by Px, Py, Pz into Imc, or in general or in short P, IE by C, with the momentum P is equal to m times u. And this P mu is also called as energy momentum 4 vector.